Hi guys, today our lesson is going to be on hybridization as we continue our study of um, covalent bonding and how to predict the shapes of our molecules. I want to talk about an important topic here called hybridization. Hybridization refers to a mixing or a blending of the atomic orbitals to make new molecular orbitals. So when the atoms mix their atomic orbitals, then they get the molecular orbitals. That's what we're going to be looking at here. So they're blending their S, their P, their D atomic orbitals. Now remember, the S orbital is spherical, the P orbital is peanut shaped, and the D orbital is double peanut shaped. So the atoms try to get an octet of electrons to stabilize um, themselves. And so if you think in terms of an s orbital, the s orbital has like one subshell that we can draw for it, or one orientation in space, and it can only hold 2 electrons, remember, with opposite spin if it's alone. So an s orbital alone cannot hold the octet of electrons. So that's where the p orbital comes in, where they're able to blend their orbitals. If you recall from our study of the p orbital has 3 orientations in space. There's the px, the py, and the pz orbital. The p orbital can hold 2, 4, 6 electrons. Remember, they fill in following Hund's rule, up, 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 and then down, down, down. So the atomic orbitals separate are your s and your p orbitals. Then you have your d orbitals. Now there are 5 orientations for the d orbital. And in this unit we've been looking at the expanded octet where the elements in the 3rd period or beyond have those empty d orbitals. So here's room for 10 more electrons if needed. But when atoms bond to form molecules, they have to mix or blend these orbitals. And that's where this idea of hybridization comes in. So we blend the hybrid orbitals to make an sp orbital, sp1, a sp2 orbital, a sp3 orbital, and we're going to also be blending with our expanded octets some of the d orbitals. So the d, meaning you're using one of your d boxes, the s and all 3 p boxes, so the dsp3 is what that's called, and the d2 sp3, where you use 2 of your d orbitals here to hold electrons. All right, so hybrid orbitals that have the same energy are called degenerate orbitals. So normally your p orbital has a little higher energy. If you're talking about the atomic orbital, it has a little higher energy than the s orbital, but whenever they blend, they become degenerate orbitals. So they're considered to have the same energy. So if you have your s orbital blending with the 3 p orbitals, this is from the s, and this is from the p. This is the px, the py, and the pz orbital that we talked about up here. And then again, if you blend those d orbitals there, okay, these are the 5 subshells for the d orbital. So this is where your d's come in. So if you blend one of your s and one of the p orbitals, we have an sp1 orbital because you're using one of the s and one of the p. So that's where the sp1 comes from. If you blend one of your s and 2 of your p subshells, sp1, p2. If you blend one of your s and all 3 of your p subshells, sp1, p2, p3. Now I am simplifying this, this is a way that you can figure it out if you're counting the sides of the atom that has something on it when you draw your Lewis structure. Now with the expanded octets, you're going to find that we're going to be sometimes using one of the d orbitals, and if so, we call it a d sp3. And if you blend 2 of your d subshells here, we call it a d2 sp3. Now, in this concept here of hybridization, you hear of hybrids with animals. Like if you were to blend or breed a poodle with a cocker spaniel, you have a cockapoo. So you have these designer dogs, if you will, that are AKC recognized. You could also have hybrid plants, hybrid cars. Hybridization just refers to when you mix or blend characteristics. So just like with the cockapoo, if you blend your s orbital, your spherical orbital, and your peanut-shaped orbital, you get a sp hybrid orbital. Notice there's a little, you still have this figure 8 shape here, but notice that one of the lobes is larger than the other lobe. This is the general shape of a sp hybrid orbital. So the types of hybrid orbitals that I just mentioned that we are going to run into are an sp, so that sounds sp1 if you want to call it that. It's when you mix one of your s subshells and one of your p subshells, utilizing two of those subshells. sp2 is when you mix one of your s and two of your p's, so one s and two of the p's gives you sp1, p2 hybrid orbital. If you mix one of your s and all three of your p subshells, that's four subshells being available to hold the electrons, you have an sp3. And then, as I said a while ago, when your d orbitals come into play and you have those expanded octets, if you're using one of those little subshells with a d, we call that a d, sp3. And if you're mixing the s, the p's, and two of your d's, that's six total subshells where you have your octahedral parent structure, D2sp3 is what we call that hybridization. Now, how to figure it out? First of all, you must be told which atom to look at. You're going to count your single bonds, your double bonds, your triple bonds, and your lone pairs one time. They're called the electron domains. So you look and see how many electron domains are around the atom that you're trying to determine the hybridization of in the molecule. So for this question here, this example says give the hybridization of carbon and CH4. So we're going to look at the carbon. Now I already have the Lewis structure drawn here. So let's look at the carbon and see how many sides of the carbon has something on it. Sort of like treat it like it's in a square box. So it's got 1, 2, 3, 4 sides with something on it. So we're going to count to 4, but instead of counting 1, 2, 3, 4, we're going to count in order S, P1, P2, and P3. sp1, p2, p3. So carbon is sp3 hybridized. It's using one of the s orbitals and all three of the p subshells. Now pause the video and see if you can do these, and then resume the video and see what you got. I'm going to continue since I only have 10 minutes. We're wanting to find the hybridization of the nitrogen, number 1. So look and see how many sides of the nitrogen has something on it. There's lone pairs here, and there's a triple bond here. So 2 of the sides of the nitrogen have something on it. So we're going to count to 2, and we're going to say sp1. So nitrogen is sp1 hybridized, or sp hybridized. Number 2, carbon. So I'm looking at this carbon here. So it has a single bond here, a single bond here, and a double bond here. 3 sides of this carbon has something on it. So sp1, p2 is the hybridization. He's sp2 hybridized. Let's look at sulfur. Sulfur has 1, 2, 3, 4, 5 sides with something on it. This has 5 electron domains. So sp1, p2, p3, and here's your D. So we're going to call it a D, sp3. We have 5 electron domains being utilized for bonding. And then finally, with the last example, iodine has 1, 2, 3, 4, 5, 6 electron domains. So sp1, p2, p3, d1, d2. When you write it, you put your D's in the front, so it's D2, sp3. All right, hope you did well on those. Let's look at this last example. Look at carbon number 1, sp1, p2, p3. He is sp3 hybridized. Carbon number 2, 1, 2, 3 sides, sp1, p2. sp2 is his hybridization. Let's look at oxygen number 1, which is here. He's got 1, 2, 3 sides with something on it. So sp1, p2 again. And finally, oxygen number 2, sp1, p2,